Hello, welcome to this lecture module on optics. In the last lecture, we discussed about reflection and refraction at a plane interface, and we discussed the Snell's law. Today, we will continue it further. In particular, we gave emphasis on light incident from air or from a rarer medium onto the interface at the denser medium and discussed about refraction and reflection. Today, this is this one when light enters from rarer medium to denser medium, that is when N1 is smaller than N2, N1 is less than N2, it is also called external reflection. Today, we will focus more on internal reflection. Internal reflection when light enters from a denser medium and is incident on the interface between the denser and rarer medium. We will see some interesting effects today. So, recall reflection and refraction at a plane interface. So, today we are looking at internal reflection, that is when N1 is greater than N2. N1 always refers to the incident medium and N2 is the second medium here. So, light, consider a point source P which is giving out light rays. The light ray which is incident normally on the interface. So, this is the denser medium, this is the rarer medium, N1 is greater than N2. The light which is ray which is incident normally, a part of it gets reflected and a part of it gets transmitted. A ray which is making an incident angle I1 here, when it goes from denser medium to rarer medium, it bends away from the normal and we can see that R1 is greater than I1. This comes out from the Snell's law. So, if I increase the angle further, that is if I consider a ray which is incident at a larger angle here, R2 further increases, R2 increases. If I increase the angle of incidence here to a value which is I3, then R3 would just graze along the interface. Every time a part of the light is reflected and a part of the light is transmitted. For the particular ray that I have shown here with an angle of incidence I3, the ray would graze along the interface, because Snell's law says sin I1 by sin R1 equal to constant, and similarly sin I2 by sin R2 equal to constant. N21 is N2 by N1, the relative refractive index. In this case N21 is less than 1 because N1 is the denser medium and N2 is the rarer medium. So, N1 is larger than N2 and therefore, N21 is less than 1. Therefore, when you write sin I2 by sin R2 equal to a quantity which is less than 1, obviously R2 is larger than I2. Now, we look at the case of I3, that is the ray which is making an angle of incidence I3, then sin I3 by sin R3 is also equal to N21, but R3 is 90 degree here, R3 because the transmitted ray or the refracted ray is grazing along the interface, therefore, R3 is 90 degree, which implies sin I3 is equal to N21, because sin R3 is 1 and therefore, sin I3 is equal to N21, which is of course less than 1. What would happen if the angle of incidence is increased beyond I3? That is, if I have another angle I4 which is greater than I3, what would be the outcome? Let us see. So, here it is. For angle I4 which is greater than I3, here I have not drawn I1, I2 those rays, I have shown the ray which is making an angle I3 here, where the transmitted ray or the refracted ray is grazing along the interface. Now, I am considering the next ray, that is a ray which is making a larger angle I4 larger than I3. What would happen? So, I have shown the reflected light here, the reflected light is there always, but I have not shown the transmitted light. What would happen? So, let us look at the mathematics. Snell's law says sin I 4 by sin R 4 must be equal to N21, but sin I 4 is greater than sin I 3 because I 4 angle here is larger than I 3. Therefore, sin I 4 is greater than sin I 3 equal to N21, but N21 is less than 1, and therefore, sin R 4 must be greater than sin R 3, which is equal to 1. This implies sin R 4 must be greater than 1. Please see this, sin I 4 is greater than sin I 3 and sin I 3 is equal to N21, that is the right hand side, and therefore, if this quantity has to be less than 1, if this ratio has to be less than 1, sin R 4 must be greater than sin I 4, and that implies sin R 4 must be greater than 1. This is not possible for any real angle R 4. Sin of an angle, the maximum value is 1 for 90 degree, and therefore, sin R 4 greater than 1 is not possible for any real angle R 4. That implies there is no refracted ray possible, while reflection is always possible. No refracted ray is possible because there is no real angle R 4 which can satisfy this, and therefore, the entire incident light energy is reflected back into the first medium. That is why I have not shown any refracted ray, because no refracted ray is possible. For all angles below I 4, there is a reflected ray and a refracted ray. As we have seen earlier, there is a reflected ray and refracted ray for I 2, I 1 and so on. But when for an angle I 4 which is greater than I 3, where the refracted ray was grazing along the interface, we do not have any refracted ray, and therefore, the entire energy has to be reflected back, and this is called total internal reflection. Sin I 3 was equal to N 2 by N 1. We have seen in the last sheet that sin I 3 was, so here sin I 3 by sin R 3 was N 2 1. So, sin I 3 was equal to N 2 1, which is N 2 by N 1, and therefore, we have sin I 3 is equal to N 2 by N 1, and the angle I 3 for which the refracted ray is grazing along the interface is called the critical angle. It is called the critical angle because for any angle larger than that, there will be no refracted ray and the entire energy or entire light energy is refracted back into the medium. Whereas, below this angle, below for angle smaller than I 3, we have both the reflected ray and the refracted ray, and therefore, this I 3 is a critical angle, a threshold angle below which refraction is possible, above which refraction is not possible, and that is why this angle is denoted by IC, called the critical angle, and therefore, IC is equal to sin inverse of N 2 by N 1. IC is nothing but I 3 in this case. So, I 3 is equal to sin inverse of N 2 by N 1, but that angle is identified as the critical angle, and therefore, the critical angle is given by sin inverse of N 2 by N 1. Okay. Let us go further. The critical angle IC, therefore, this was I 3 in my first figure, sin IC is equal to N 2 1, which is equal to N 2 by N 1, and therefore, IC is equal to sin inverse of N 2 by N 1, with of course, N 2 less than N 1. So, typical values of IC for the medium air interface, we have a medium and the other side air. So, this way the medium air interface is given by IC is equal to sin inverse of 1 by n medium, because n air is 1, n 2 is n air which is 1, and therefore, IC is sin inverse 1 by the refractive index of the medium. So, I have taken 3 different values here. So, 3 different media: crown glass, water and diamond. So, for crown glass the refractive index is 1.52 approximately. Glass is a very generic word, and even within crown glass there are different varieties with the different refractive index, but this is a typical value of crown refractive index of crown glass. The corresponding IC calculated from here is approximately 41 degrees. For water with refractive index 1.33, the critical angle is 48.8 degrees, and for diamond with a refractive index of 2.42, the critical angle is 24.4 degrees. What we observe is that as the refractive index of the medium, that is the denser medium, increases, the critical angle decreases. We can see from here, as the refractive index increases, the critical angle decreases. For smaller values of N21, the critical angle will be smaller. Let us see a couple of examples here. First, let me take out reflection by a prism. So, what I have shown here is a 90-degree prism with, it is an isosceles prism with 45-degree and 45-degree angles here. A laser beam which is entering from here, a laser beam that is entering will subtend an angle of 45 degree here, because a laser beam entering normally this angle is 90 degree, and therefore, this angle has to be 45 degree if this is 45 degree, and therefore, this angle of incidence is greater than the critical angle. Critical angle we just calculated, it was 41 degree, and the angle of incidence I is 45 degree, therefore, I is greater than IC. This implies the beam will have to undergo total internal reflection. So, there is the beam undergoing total internal reflection, and this is now deflected into 90 degree angle, that is the direction of the beam has changed. If we keep the prism in this way, then we see that the incident angle is again 45 degree here, this is 90 degree, therefore, light gets transmitted. Of course, there is a small fraction which is getting reflected here, but we are looking at the transmitted light. Most of the light is transmitted, a small fraction is reflected. It undergoes total internal reflection, therefore, again the angle here is 45 degree, therefore, it undergoes total internal reflection here, and the beam is reversed in direction. So, it has come like this, and now it is reflected back along the same direction. That is why it is also called retro reflectors. So, these are used widely in various applications. So, I will just show you the prism, and we will discuss about this a little later. So, here is the prism. So, let me keep the prism here. So, we can see, I hope we will be able to see like this. So, it has two reflecting surfaces, one here and one here, and the third one here along the hypotenuse. So, in the first example, I launched the laser beam along this direction, and the beam would come in this direction, and if we launch the laser beam like this, that is along this direction, it would undergo total internal reflection at this point, and again undergo total internal reflection and come back along this direction. There are various applications of these beam deflectors, because many times the laser cannot be moved, laser is fixed at a particular location, particularly higher power lasers, and then you have to deflect the beam to another direction to perform maybe another experiment, and then we easily use such prisms to deflect the beam in the required direction. Of course, one could use mirrors, but all mirrors have a finite amount of loss, therefore, the reflected light gets lost somewhat and a fraction only is reflected back. Whereas, using this prism we are having 90 degree reflection, but it is total internal reflection, therefore, the entire beam is reflected back. That is why people use such prisms for deflecting beams rather than mirrors. Okay, let us go further. Let us extend the example further now to a slab, internal reflection in a glass slab. So, I have taken this glass slab here. So, this is the glass slab. Earlier we discussed internal reflection at one interface. Now, basically I have added one more interface. Therefore, this is a denser medium glass. Light is now not entering, I am not considering the case of light entering from here, because if light enters from here, it will pass through with a small lateral shift. But we are looking at light entering from the edge of the glass slab. So, this is the glass slab and light is entering from one of the edges. So, look at the rays 1, 2, 3, I have marked 1, 2, 3. The ray 1 which enters from here bends towards the normal, because this is air, this is glass, therefore, it undergoes partial reflection. So, it bends towards the normal. So, the refracted ray comes here. If the angle of incidence here is greater than the critical angle, it will get totally internally reflected, because on the other side there is air. So, glass air interface, and therefore, total internal reflection can take place. Here total internal reflection cannot take place, because it is rarer medium to denser medium, that is external reflection, whereas this is internal reflection. Similarly, if I look at a slightly, I am increasing the angle of incidence. So, this was the angle of incidence. Now, if I increase the angle of incidence, look at the ray 2, it also bends towards the normal. However, now it is subtending slightly larger angle I 2, smaller angle compared to I 3 here. I 2 is smaller, but if I 2 is greater than the critical angle, then it will also undergo total internal reflection. And if it subtends an angle I 2 here, it will also subtend an angle I 2 and it will undergo total internal reflection, because these are two parallel lines, and therefore, if this is I 2, then this will also be I 2, which means if it undergoes total internal reflection here, it will also undergo total internal reflection here, and the light will get transmitted inside the slab. If we look at the ray 3, which is now coming at a larger angle, of course, the ray bends towards the normal, but now it is incident at an angle I 1, it is shown here I 1, this angle of incidence is such that I 1 is smaller than the critical angle. Then a part of the light will be refracted, I have shown it as 3 dash, ray 3 entering here, and it is 3 dash is the refracted light, and it also gets reflected. So, a part of the light is getting reflected, it will subtend the same angle I 1, which is less than the critical angle. Therefore, again a part will be transmitted or refracted and a part will be reflected. So, it will undergo reflection, partial reflections at every interface, and at every interface it will lose a part of the energy, and the remaining part proceeds further. Whereas, ray 1 and 2 do not lose any energy when it undergoes reflection, and therefore, they get trapped inside the slab. That is what is being written here. I 1 is less than I c for glass air interface, undergoes partial reflection, while I 2, I 3 are greater than I c, which undergo total internal reflection. All rays like 1, 2, for which I is greater than I c at the glass air interface, propagate totally inside the glass slab. This is the principle of light propagation in optical fibers. So, we will see optical fibers. What are optical fibers? This is our next topic. So, optical fiber here. So, an optical fiber comprises of two cylinders here, that is a central core surrounded by a cladding. Both are glass cylinders which are fused into one another, they are not separable. It is not a hollow core, this is also glass, this is also glass, which are fused one into another, and the refractive index of the core here is greater than refractive index of the outer medium, which is the cladding. Cladding is something which is covering, so that is why it is called cladding. The refractive index N core is greater than N clad. Typical dimensions are given. So, the dimension of the core is typically 50 micrometer and the cladding diameter is approximately 125 micrometer for standard fibers. There are different types of fibers which are used and they will have different dimensions, different refractive indexes. But in general, the material used, particularly for communication fibers, the material used is core is of doped silica glass. Silica is SiO2 or fused quartz, doped silica glass and typical refractive index of about 1.48, and the cladding comprises of pure silica glass and the refractive index is approximately 1.42. This is silica, silica is SiO2, also called fused quartz. So, light propagates by total internal reflection at the core cladding interface. So, what I have shown here is a longitudinal section of this fiber. So, a section here, longitudinal section. So, this is the end face here. So, light input undergoes total internal reflection along its length at the core cladding interface, and therefore, light gets trapped. Obviously, if I launch light at a larger angle here, the incident angle, then it may not be able to meet the condition for total internal reflection at this interface. In this case, a part of the light will go out, that is, will refract out, and only a part of the light will get transmitted. So, there is a range of angles, I can show here a range of angles. So, I can show a range of angles for which light gets trapped. So, it forms a cone like this here and light gets trapped inside. So, there are large number of applications of optical fibers and I have just listed a few of the applications here, applications of optical fibers. Optical fiber, the most important application which we are all familiar is the optical fiber communication as a transmission medium for multi-gigabit signals, audio, video, telephonic conversations in all major cities, and major cities are now linked by optical fibers, and each fiber is able to carry gigabits of information, and that is the primary main application of optical fibers. And there are many other applications, optical fiber sensors for a variety of sensors for industrial and scientific applications, optical fiber lasers to develop high power laser sources, high power optical sources for industrial and military applications, and endoscopy, which is one of the earliest applications of optical fibers as a fiber guide or a tube for image transmission. These are fiber guides used to observe internal parts of the body, and that is called endoscopy. And of course, there are large number of applications I have not listed here. Each one of the application is a very important technology now. So, here I have a laser and a prism, and I just want to demonstrate to you the retroreflector. See, if I switch on the laser here, we can see the beam is completely getting reflected back here, because it is undergoing total internal reflection at both the interfaces, that is here as well as here, and this is the principle of a retroreflector. We can see here that it is following exactly the same path. This is the input beam which I have blocked now, and this is the reflected beam, and there is no output light here, there is no laser beam on both the sides here. However, if I change the angle of incidence so that the angle of incidence is, so we can see, so it is continuously reflecting. Now, I am changing the angle of incidence so that it does not meet the condition, then immediately you see the light, reflected light has dropped down and there is transmitted light which is here, the transmitted light coming from the other side. So, we have refracted light as well as the reflected light, both of them. However, if I bring it here such that the angle of incidence is 45 degree, this is an isosceles triangle, then all the light is reflected, there is no light on the other side. I can also demonstrate this here, that is the beam deflector. So, I keep it here. Actually, the prism is a little bit bigger size, but we can see here clearly that here it is, and the reflected line is here, and the incident beam is completely deflected at 90 degrees. There is nothing on the other side, we can see here there is no beam, entire energy is reflected, because the ray enters from here, the beam enters from the input end, and it undergoes total internal reflection at this end and comes out as shown in this diagram. I also want to briefly show you the optical fiber. So, here is an optical fiber. For those of you who have not seen an optical fiber, maybe you will see this as a shining medium here, and you can see this is an optical fiber, and I can try to couple light into one end and see whether we can get some output at the other end. So, what I am trying to do is I am keeping the prism as a paperweight, do not look at the prism. I am now trying to launch light from the other end. Let me just give it a try, and if light enters the fiber, then we should see a brighter spot at this end. So, let me try this. So, at some point when I am able to launch light, you see suddenly a bright light which is coming there, because I do not have a arrangement to hold it in position, and therefore, only when in some positions you can see that it looks bright, because light enters through the fiber as at a certain position, and we are able to see at the other end. So, what you see is light coming from the other end of the fiber. Yeah. So, there it is, and let us continue now further. Let me now come to a naturally occurring phenomena, where we observe mirage. So, what is a mirage? Mirage, an optical illusion. So, first I have shown here what is a mirage for those of you who are not familiar. When a person is walking through plains or desert, or even walking or driving along a straight road such as highway on a hot sunny day, he observes mirage, he could observe mirage depending on his position. So, what I have illustrated here is a tree, a distant tree. Here is a person who is walking, here is a distant tree. The person observes a virtual image of the tree because of a phenomena called mirage. So, how does he observe this? We will discuss this in detail in the next slide, but first, so he observes a virtual image, and therefore, he thinks probably there is water or some reflecting medium here on his way. So, obviously, on the way there may not be any mirror or anything. So, it appears as if there is a water body, because of which he is observing the image of this tree, but actually there is no water. What is happening is a phenomena which we call mirage. So, I have briefly shown here what is happening is the rays which come out, or rays which start from the object, take a curved path, and it gives an illusion, or it gives a feeling of apparent position of the tree which is here. So, because the ray follow a curved path and they enter the eye from below after after curving like this, the person feels as if the rays are coming from here. So, it is like a virtual ray entering his eye. So, it is as if they are coming from here, and therefore, he sees a virtual image of the object. So, why does the ray bend here? Because on a hot day, the surface of the earth becomes very hot, the air becomes hot, the air in contact with the surface of the earth becomes hot, and of course, it rises up because of convection, and the colder air comes down, and after some time there is a kind of temperature distribution here, and we have hot air very close to the surface, a little less hotter air a little less above, a little above, and a little lesser hot air above, and so on. So, I will discuss this in more detail, and this leads to a refractive index gradient, and therefore, the ray paths start curving. So, I will explain this in the next slide on. So, let us first look at ray paths in a graded index medium. I have taken two media, uniform media, which means uniform refractive index, which means the refractive index is constant everywhere. In such media, ray paths are straight lines. Point P here, let us say this is a source point from which rays are travelling and rays are emanated. So, the rays travel in straight lines in a uniform media. What would happen if the source is now in a graded index media, graded refractive index media or graded index medium? What I have shown here is the refractive index variation. So, this is n of y, refractive index as a function of y is the depth here. So, as we come down, the refractive index decreases. So, in this medium refractive index was constant everywhere. In this medium, refractive index is maximum here, and as we come down, the refractive index drops down, refractive index comes down, and such a medium is called graded index medium. The consequence of this is a ray which is emanated from the point P starts curving, starts bending, or the ray paths are curved in such a graded index media. So, we can understand this here. So, here in another diagram, what I have shown is the refractive index is highest here, it is reducing continuously as we go down. See this, refractive index is maximum here near the surface, and then it is continuously dropping down. So, if we consider this medium to be stratified, if we imagine this to comprise of number of layers, number of uniform layers, that is each layer we can consider to be of uniform refractive index, but this layer is of higher index compared to this layer, and this layer is of lower index compared to the refractive index of this medium. What would happen? We can show that a ray which is entering here, it satisfies the Snell's law. So, it bends away from the normal because this medium is of lower refractive index. Again it bends away from the normal. So, this we have shown piecewise continuous straight lines, piecewise continuous straight lines, because these media, each one of them is of uniform refractive index, but the refractive index of a lower layer is smaller compared to the refractive index of a higher layer, a layer which is here, and therefore, at every interface the ray bends away from the normal. So, if we now look at the overall ray path, it has bent, it is not a straight line path, but it has curved like this. Keeping this in mind, now we look back at the formation of Mirage again. So, I briefly explained earlier, now let us look back keeping this idea in mind. So, let us see. I have now shown a object like this, like a lighthouse here. The observer is at a distance this is the earth and this is the atmosphere. It is a hot sunny day. Therefore, if we look at the air temperature, it is hottest closest to the earth surface and then reduces. So, I have written this as warm, warmer, hot, hottest. The refractive index reduces as temperature increases. Cold air has a higher refractive index compared to hot air, and therefore, the refractive index here n as temperature increases, refractive index decreases. Therefore, the refractive index n of this medium is a function of temperature, which means the refractive index here is lower, is higher compared to the refractive index here, because this is hotter and therefore, refractive index is lower. This is hotter compared to this and therefore, the refractive index is lower. So, essentially I have a graded index medium with the highest refractive index here and refractive index dropping as I go below. And I have picked up 3 points from the object. So, a ray 3, ray 2 and ray 1 starting from different points on the object. So, this is the object like a lighthouse seal, for example. The ray which travels from here travels, it is traveling at an angle and therefore, it is continuously bending towards higher refractive index and it comes here. A ray which is traveling from here is going from higher refractive index to lower refractive index, higher to lower, and therefore, it continuously bends away from the normal. Instead of going straight like this, it bends away from the normal, and finally, it comes here to the observer. Now, the observer sees as if the rays are coming from somewhere here, because the ray which was coming like this is now entering his eye from below, and therefore, he looks at the object as if the object is here. Consequently, he sees a virtual image because of the bending of rays. There is no reflection, there are no mirrors here, but because of the bending of the rays, the apparent position of the object, the observer sees the apparent position of the object to be here, which is like having a reflection. So, if I had a mirror here, then rays would have come here and it would have reflected back. For example, on the road, if I instead of the road, so the observer is here. If this were to be a mirror and if I had the object here, so I am trying to draw the same object here, then if this is an object point, ray which comes here would have reflected and gone to his eyes here. Then he would have seen that this as if the ray has come from a point here. If I pick up another ray, then this ray would hit some point and would get reflected and here, and he would see as if the point is here, the object point. This is the object point, this is another object point, but they are now visible here if this was a mirror. But these are all straight line paths. Now, we do not have a mirror, but we have a graded index medium. So, the ray bends and enters his eye from below, and this gives the same feeling as if he is seeing an image which is here, and therefore, it gives a feeling to the observer as if on the road there is some reflecting surface or such as water, and that is why it is called a mirage. Mirage, because there is no water, but it gives a feeling to the observer as if there is water, and as he goes closer and closer, the water body, the apparent water body moves away from him, because actually there is no water. So, this is the formation of image, mirage. Using two concepts we have used, one, curved ray paths in a graded index media and apparent position of an object. because it comes like this. However, please see that if the observer raises his head and looks at the tower here, he will not see a mirage, he will be directly able to see the object here. If he looks up and looks at the object, he will be able to see the tree or the cloud, but if he is looking down, then he will also be able to see the image of the clouds or the tree because of the mirage. Let us take some examples now and make our concepts a bit more clearer. So, first I have picked up an exercise here from the textbook. At what angle should a ray of light be incident on the face of a prism of refracting angle 60 degree, so that it just suffers total internal reflection, just suffers total internal reflection at the other face. The refractive index of the material of the prism is given 1.524. So, I have here drawn the figure and tried to explain this so that we can comprehend the problem. So, a ray of light is entering from here at a certain angle I, it gets refracted into the prism, and if the question is what is this I, if there is refraction taking place at the other interface such that it is undergoing total internal reflection, just means our angle of incidence here is critical angle. When this is critical angle, the refracted ray will graze through the interface. If I were to take another ray here, a deeper ray which is incident like this, then it would have gone here like this, and obviously it would not meet the IC and this would come here. So, if I decrease this I, so this was for a larger angle of incidence, if I decrease this I, then the refracted ray comes here, and at one stage this angle here would be large enough so that it undergoes total internal reflection. Any further, if I had reduced the angle here to a smaller value, then it would have hit here. So, let me show you the, if I had taken, let me take another ray, if I had taken a ray here, then it would have come here at a different angle and this would have undergone total internal reflection. There would have been no refracted ray. So, the question here is what is this angle I, so that please look at the blue line only, blue ray, so that the refracted ray is just grazing the other surface. So, identify, so what needs to be identified? So, let me work this out. So, let us work out the solution here. So, solution. So, let me draw the prism here. So, what is given is this angle is 60 degree, 60 degree. So, we have a ray which is incident. So, let me use a different color like this. This is undergoing refraction and then this is grazing through this surface. So, if I show the normals here, I am drawing the same diagram again. These are the normals. Then we have, this is I, let me show this. This is the angle of incidence I, which we have to find out, and what is the data that we have. So, this, there are two refracting angles here. So, let me call this one as R1 and this angle here as R2, R1 and R2, and let me draw this angle here as theta 1 and this angle theta 2, theta 2. So, look at the diagram here. I hope the diagram is clear. So, we can if required we can draw a bigger diagram. So, here let me show afresh a little bit bigger. And grazing like this. So, this is 60 degree. So, I have called this as theta 1, this is theta 1, this is r 1, the refracted angle, this is I and this is r 2, because this will become the incident angle and this as theta. So, let us look at the first. It is given that it is just undergoing total internal reflection, which means R 2 is the critical angle. This is the main point to be identified. R 2 is the critical angle for glass air interface. So, critical angle. The refractive index is given 1.524 and therefore, R 2 is equal to sine inverse of n 2 by n 1. So, it is here. So, we have 1, outside it is 1, therefore, 1 divided by 1.524. So, if you calculate this, this will come out to be 41 degree, because we have already seen that the critical angle is about 41 degree. So, this is 41 degree, actually 41 point some 00 something like that. So, we have got R 2. Once we know R 2, we can find out theta 2, because theta 2 now is equal to 90 degree minus R 2, which is equal to 90 degree minus 41 degree, which is equal to 49 degrees. If we know theta 2, we know theta 1, because 60 is the angle is given. Therefore, theta 1 is equal to, so it is 180 minus 60 minus 49 degrees, and therefore, this is equal to, so 180 minus 60 minus 41. So, this is 120 minus 49 and therefore, it is 71 degrees. Once we know theta 1, we know what is R 1, because this is 90 degree, this is normal, and therefore, R 1 is equal to 90 minus theta 1, which is equal to 19 degree. So, we have got 19 degree. We have got R 1. How to get I? Simply apply Snell's law, and therefore, so let me continue here in the sheet, and therefore, sin I by sin R 1 is equal to n 2 by n 1. So, 1.524 divided by 1. We know R 1 is 90 degree, therefore, I is equal to sine inverse. I have taken this to the other side and then inverse of this. So, sine inverse of sine R. So, this I had taken here sine R 1 into 1.524. So, this is equal to sine inverse of sine 90 degree, sine 19 degree into 1.524. So, this will come out to be 29.75 degrees. So, this was the angle that was asked to find out. So, we see here. So, what is this angle? So, what we have done? We have used two concepts here. One, total internal reflection here and Snell's law here. We have applied a total internal reflection and Snell's law. Using these two concepts, we can solve this and get the angle I such that it is grazing along the second interface. Let me take a second example now, and this time let me take an example on optical fiber. So, here given that the refractive index of the core of an optical fiber, here the refractive index of the core of an optical fiber is 1.48, I just used this number earlier, and that of the cladding is 1.46. What is the maximum angle of incidence of rays, angle with the axis of the fiber at the input, that is at the input end of the fiber, the maximum angle with the axis for which they are guided through the fiber. The question is to determine what is the maximum angle for which the rays inside are guided. If we launch a ray along the axis, it will anyhow get into the fiber because it is normally incidence angle is 0. If you increase this angle, then it will start bending here, and therefore, one has to note down. So, let me draw the cross section and show you this more carefully. Let me take a longitudinal section here and show this more carefully. So, what is the data which is given? So, we have here this is the optical fiber. So, it is given that refractive index is 1.46, 1.48 and 1.46, because this is the outer layer which is the cladding and this is the core layer. So, here is the fiber axis. So, this is the fiber axis. A ray which is incident here. So, we are looking for a ray. So, let me use a different red color for this. So, a ray which undergoes just total internal reflection. It is bending towards normal because outside it is air. So, we have air here and outside it is air. Therefore, this ray is bending towards normal and it is just undergoing total internal reflection, which means this is grazing along this. In other words, if I take another ray which is coming here, so this is the angle I max that we need to find out. So, this is I or I max. Why do I say that that is I max? Because if I take a ray here, then that is the second ray that will bend closer because that is at a smaller angle, and therefore, obviously for if this is the critical angle. So, here I have the critical angle. So, let me show the normal at this point. Then this angle here is the critical angle. A ray which is travelling like this will obviously make an angle which is more than the critical angle here, and therefore, it will get totally internally reflected. This is just like the diagram that I had already shown, the diagram which I had shown earlier with when I discussed about optical fibers. So, let me just place that diagram to make it more clear. So, here. So, a ray which is incident at a deeper angle would undergo partial reflection, whereas rays which are coming at shallower angles would meet the condition of total internal reflection. So, the question is asking about the I max for which there is graded grazing, the refracted ray is grazing along the interface. So, this angle must be equal to, this angle here must be equal to IC or the critical angle. So, if we focus at this point, so let me draw that again, just this point. If I zoom that point, so here is the ray which is incident and this is grazing, and here is the normal and this is IC, and corresponding to this I have an Imax here. So, we know the refractive index here 1.46, 1.48, and therefore, we can determine what is IC. So, IC is equal to sine inverse of 1.46 by 1.48. So, this will come out to be I think 80 point some number, which 80.57. So, 80.57 degrees. So, the angle I see here is 80.57. If this is the angle I see, then we can determine what is the refracted angle. So, this if I show this as my input, then I can determine the refracted angle here. So, this is R, this was IC which is 80.57, and therefore, the refracted angle at the input corresponding to this Imax here is R is equal to 90 minus 80.57, which is equal to 9.43 degree. Once I know R, I can determine the Imax angle which is coming here. So, this is Imax, the angle Imax here. We simply apply Snell's law for this interface. I know this R, and therefore, I can determine Imax. So, Imax will be equal to, so let me show here, therefore, sin Imax by sin R is equal to N2 by N1. So, let me write here sin Imax divided by sin R is equal to 1.48 N2 by N1. This is N2, this is N1, this outside it is air 1.0 and 1.48, and therefore, it is 1.48 divided by 1.0, and therefore, Imax is equal to sine inverse, this goes there. So, sine inverse of sin R, R is 9.43 degrees. So, 9.43 degrees multiplied by 1.48. So, sine of 9.43 multiplied by 1.8. So, we should get this as about 14 degree, 14.03 degrees. One can work out many problems, and I will stop here, and I encourage you to work out as many problems as possible. Thank you.